Let me introduce the keynote speaker to you. Architect Nirodha Gunadasa is the director of Arcadium Limited, a leading design consultancy practice in Colombo, Sri Lanka. He is a chartered architect practicing in Colombo and a resource person for the MSc program in Sustainable Built Environment, University of Peradeniya. He has been the principal architect of several landmark high-rise development in Colombo City, including the 75-story Horton Square project. His field of specialism is the design of tall buildings and sustainable design. Over to you, sir.
Right, okay. So good morning, everybody. So let's begin. So my topic, I think he spelled it a little wrong. So I'm going to talk about tall buildings, the design technology of future. So that is my topic. So let's begin. Okay, so we'll start with nature. Actually, nature by nature is very, very complicated. So what is this? This is the standard model Lagrangian. So if you look at it, it's a very, very complicated thing. And it can explain everything, every phenomena known to human beings of quantum scale. So from laser to nuclear explosions to superconductors, everything can be precisely calculated and then explained with this. But it's a huge, complicated thing. At cosmic level also, nature is very, very complicated. So this is the Einstein's field equation. So it is a little simple because this mu nu notation system. Otherwise, if we expand this, this is also an equally complicated thing. But we who design tall buildings, for us, nature is not so complicated. We work at classical scale. So for us, nature is not so complicated. Nature works on a very simple principle. It's F equals ma. But you might say there are three principles, so Newton has three laws. But all those three laws just mean nothing else but F equals ma. So that's the principle we work on. And in this F equals ma, this A is a mechanical engineer's thing. So when I say that, I think most of you are structural engineers, you might argue with me. We also work with A, so we work with seismic loads, we work with wind, we work with blasts, so natural frequencies we work on, so we are working with A. It's true that structural engineers also work with acceleration, but it's not really your territory. So fundamentally, for structural engineers, this A is 0. So you are left with a very simple, nice equation, isn't it? This is what you work with, F equals 0. So all these shear forces we are talking about, bending moments, all those stems from F equals 0. And if you want, you can forget those jargon and you can start from this and do everything with this. So F equals 0, that is all that you know, and that is all you need to know. So when I say these kind of satirical things, you might ask, you are an architect, what is your equation? So what is architect's equation? So I also have an equation. Yeah, it is also F equals ma. And as I said, this A belongs to mechanical engineers. So we are very generous, so we are so happy that mechanical engineers is there to look after this A. So take it off, it is your duty, it's not mine. I'm so happy. So I'm also left with this simple equation of structural engineers, F equals ma. F equals 0. And as I said, this is structural engineers thing, so I'm so happy you are there to take care of F, so my life is easy, so take it away. And this is my equation. Simple, nice equation, 0 equals 0. And this is expression, if I want, I can simplify even further. So this is architect's expression. It's 0. Okay, so what I'm going to do is, this is what we deal with as architects. 0. We work with space without time and also forces. What we work with is, we work with pure space and form. So that is what we work with. So I'm going to illustrate what we are doing, what we can do with pure space and form, actually with zero, what we can do. Okay. So this is empty space. And what is this? For you, it's a point in space. And for us who do graphics and architects, it's not a point in space, it's a vector. So you might, those who don't know, might think, how can a point be a vector? It is possible when you consider there is a origin point of a coordinate system. So if there's the origin point of a coordinate system, in relation to the origin point, it has a direction and also it has a magnitude. So a point can be a vector. But the problem is for us, this vector by definition, it doesn't have a position in space. So that one, this one and this one, all those are same vector. It has a magnitude, it has a direction, but it doesn't have a position in space. So we can't work with them. So we are not working with this kind of vectors. This is the kind of vectors we work with. It has x component, y component, z component, and also a number one. This number one has something to do with graphically fixing this vector on space. But mathematically what we are doing is we are actually moving the origin point of the vector and not the vector. So yeah, the theory remains still as it is. The vector doesn't have a position. Since this has four elements here, we can't work with 2 by 2 matrices. We have to work with 4 by 4 matrices. So this is your commonly known 3 by 3 matrix, and we have this large matrix. And this particular numbers, what they do is they just graphically translate the vector. Okay, that's a little simple thing. And then this is a set of vectors x0, 0, 1. So x varies from 0 to 1000, let's say. So it's a group of vectors. So when I multiply this vector by the identity matrix, nothing happens. But I change that number to x. And then what will happen is this 0 stays there, but 1 moves to 1, 2 moves to 2, and so forth. This vector gets translated. So that's what we do. So instead of x, if we put sin x, it becomes a curve like that. And if I add a multiplier like that for that one, this starts to play. So it's fun to work with these matrices and vectors. So this is amplitude of the wave changing. And instead of there, if you put a number there in front of x and then play with that variable, I can play with the frequency of the thing. Okay, so in the z direction, if I put cos x and I turn this to 3D space, yeah, it becomes a spiral then. So as it changes the height of x direction, it changes to the z direction as well. So it spirals out. So likewise, just with 0 space, just space, there are a lot of things we can do with. So this is the same matrix. I'll multiply the matrix with the scalar matrix, you know. Then this thing becomes something much more interesting. So it's the same spiral I talked about. We have just playing with the scale of it. So it's bigger here, it becomes smaller there, and as it grows, it increases once again. So it creates very beautiful forms. So likewise, it's just with few numbers on matrices, we play with forms. And the important thing is, what is this? This is a region in space. So it has x, y, and z. So let's say x is 0 to 10, y is 0 to 10, and z is 0 to maybe 100. So if you do the same thing, this is the same matrix. If you multiply that group of vectors with that, it starts to play. Right, so this time I will use the shear matrix instead of the distance, and it becomes something very interesting and unique. So it's a beautiful play. You can see how it shears and it transforms the space just by adding sin x and cos x, and it shears sin x this direction, cos x this direction. So I can do more with this. The same matrix, if I multiply with another matrix, I'll just multiply the scalar matrix we talked about earlier. We just scale the things up. And I can then taper it up, give it different forms. So if I want, I can tape it like that as well. So very, very interesting forms we can create out of it. Right. So I talked about all this, it is because a building itself is a region of space. And what happens is it takes forms under various influences. And as architects, what we do is we identify those influences and we give form to building. So this, for example, is a building. So I have shown this last time also. So the height is a variable. So as the height varies, you can see how everything changes. But it doesn't just increase the height. So if you look at the lobby space at the ground level, as the height increases, the requirement of lobby space increases. So all those things are built into matrices. And then when we apply it, we can play with one variable, and all other things automatically get adjusted. So that is the technology we use to design these days. So this one, just to show you, I have put a sine curve to wave it. So it varies the width of the building. But you can see as the width increases, the windows are appearing and they're disappearing. So as the width is less, windows goes out. So it's programmed in that way. So when there's a large floor plate, you need outside ventilation more. So it is programmed in such a way with matrices, so it adapts. So this is the same thing. We have built in climate to it. So as the climate changes, this is how this building starts to respond to climate. So in tropical climate, you need a lot of openings, lot of overhangs. So when the climate changes, it opens up, it gives out overhangs. And when it goes to a colder climate, it reduces the windows. So that's how it works. Actually, because of this matrix system, we can apply one matrix over another matrix over another matrix. So we have no problem considering the transformation in terms of climate, in terms of many other factors, and then work with it. Right, so I think I explained how we design buildings with modern design technology. So it's simple. The first one is very simple. We identify the parameters that shall form the building. That is the first thing. So there are many parameters. For example, the form of the site is a parameter, land value is a parameter, climatic conditions are parameters, the culture, the human behavior is a parameter. All those are parameters. Second one is we build them up to matrices and equations. And the third one is very easy. We just let those parameters multiply each other and then give the form to the building. But the second one, build them into matrices and equations. Is it possible? Is this an easy thing? If you ask me, can you do it? The answer is, actually, no, I can't do it. I don't know how to do it. Some things I can. Site form, definitely I can translate to that. The land value I can. But human behavior, culture kind of things, there are no ways. So actually the things that we should translate, that should give form to a building, if it is like this, I can deal with, but what I can deal is only something like this. So many things we can't deal today. You can do many things. It is because you have a genius behind you, isn't it? So he looked at an apple fall and he said F equals ma. So this is a group of people moving. So they move in different ways. So one is hanging onto phone, one is just mesmerized with the beauty. And the way people move change from London to Colombo and from Colombo Mathura. I don't have a genius behind me to look at this and then say F equals ma. So I don't know how people behave. So climate, culture, behavior, so we can't do it because we don't have a genius behind us today. But the good news is that genius is coming. It's coming. It's coming in the form of neural networks. So I'd like to explain neural networks from the beginning, but I'm not going to do that. Last time professor said he's going to give me 1 hour next year, so I was prepared for that. So he's just giving me 15 minutes, so I can't do that. So neural networks, and I would like to explain the physics informed neural networks, how they work. I'm not going to do that. And under that, there's a subset called SINDIS. SINDIS is about sparse identification of nonlinear dynamics. I'm not going to explain what it is. What I'm going to tell you what it does. What it does is when there's a system, if you give the system, this is the neural network, if you give the positions and velocities of any kind of a system, it can study it and then come up with the governing equation behind that. The most simplest equation, it will come out. For example, if you show an apple falling, a video, if you just upload it, it is going to tell you F equals ma. So that is what SINDIS does, and they are developing in a very big way. So this is a very complicated system, the butterfly system, I think you know. So this is something structural engineers are very familiar with. So when you just insert the positions and velocities of these systems, it splits out the governing equations in a very successful manner. So this is the news. So when these things are developed in near future, we will be able to model and interpret very, very complex systems. Complex systems like climate, human behavior, like culture, and like things like stock market. So those things we will be able to deal with, and we will be able to model much, much more meaningful tall buildings in future. So that's my talk. Thank you.